So today we're going to have, I think, a shorter kind of lesson, and I think that most of what we're going to talk about, some of you at least would already know. I think that some of the material that we are covering today shouldn't be that much new. Just a moment. So we're going to be talking about numerical systems and how things are represented in memory. And I think that this is coming a bit, personally I think this is coming a little bit too late, because in the previous part of the course you guys have already been doing some kick-ass binary manipulations on some things, and even though we haven't gone down to the small details, so we're going to go a little bit more down into details. I think it's going to be quite short. There is a part which is not covered in the presentation, and I'm going to give it a little bit, just going half a step a little bit deeper with it, to show you a little bit about floating point numbers and the amount of headache that they can cause. I think we're going to be a little bit short, and if anything is not clear, of course, feel free to stop me and ask whenever you need some clarifications. It will be more clear than the previous lesson that was a little bit off with the presentation, that I think wasn't matching much of the demos, and the data in the presentation was a little bit much forward than what we actually needed. So today there's not going to be a lot of demos. We're going to talk a little bit more about just a little more theoretically, and starting from the next lesson I think we're going to start diving into the serious business, which is methods and classes and recursions and a lot of fun. So we're going to be talking about representation mostly of numbers. Again, some of this you already know, it's been covered. You know that numbers are represented binary, in binary forms. You know that they could be represented, probably you know already that they could be represented in short with hexadecimal formats, just because it makes it much easier. So we'll dive into looking at those. We'll see a little bit of floating point numbers, and we'll see how they are structured a little bit ahead of what is included in this presentation, because I think it's not extremely clear the way that it's presented here. So we're going to look at it a little bit deeper. And the text, which there's not much to say about, that it's just a collection of characters, and you know that already too, because you've been handling text and strings. So without further ado, let's go on, unless someone has already a question. So the regular numbers that we use in the everyday life, it's important because this material is the base of all computer operations and how computers analyze and how computers understand the data which is given to them. In everyday life, we usually, unless you are extremely geeky, we use the base 10 to represent numbers. That means we have 10 different symbols that can represent parts of the number. Oops. So if we look, for example, at a number called like this number 401, is it working? Not very much. So we can see that every place in the number where we have a character, it represents the power of 10. Since we have, what's going on here? Since we have 10 different symbols to represent numbers, these are the numbers from 0 to 9, we can represent each number in its place by a power of 10. So the first number will be times 10 in the power of 0, and every number in the power of 0 is 1. Then the second will be timed the 10 in the number of 1, and then 10 in the power of 2. So that's how we actually construct our numbers, and that's how we get to the representation of 401. That means 1 time 0, 1 time 1, 0 time 10, and 4 time 100. Is this clear to everyone? Mm-hmm. Same we see here. So we have 0 times 1, and then 3 times 10, and then 1 times 100. And you can see that the structure here is consistent. We're going from 10 in the second, then 10 in the first, and 10 in 0 powers, and we can actually calculate what is the result. And the same here with the 9786. Same thing. Not much to say about that, right? This is the everyday numbers, and that's how they're structured. Computers, however, are not as smart, and they have only representations of zeros and ones, which can be parsed as true or false, or on or off. So these are actually bits, binary digits. Bit is a short form for binary digit. And we can represent a series of bits like this, so we can see which of the switches in this visualization is turned on and which is turned off, and we can construct a series of bits, and that's really what goes into the machine. That's what sits in the memory, and that's what computers can read and write and understand. And with these bits we have to represent everything, all the data. That includes strings, that includes characters, that includes complicated numbers like floating points, big numbers, but you know all that, right? Did I stop the recording? I hope not. Okay. Okay, so we see two different examples of switches. I just didn't know there were sound effects here too. Binary representation pretty much follows the same rules that we know from decimal representation. That means that since we have only two symbols that can represent a number, and in the computer world they are usually referred to as 0 and 1, in the electronic world they are referred to there is or there isn't any current passing. So we have the 0 and the 1 representing numbers, and we are counting in the base of 2. That means that every spot, every place which it constructs the number relies on the power of 2. So the first one will be 2 in the power of 0, and the second will be 2 in the power of 1, and then 2 in the power of 2. So the first digit will represent how many ones, and the second digit will represent 2, and the third digit will represent 4. So in this case we have 1, 0, 1. We can see that this corresponds to 4, and then 0 times 2, and then 1 times 1, which is 4 and 1. That means this represents 5. Is this clear? Am I going too fast with this, or too slow, or is it okay? So the other examples here are the same. We are starting from the right side. That's usually referred to as the least significant bit of the number, and we're going towards the left, which is usually referred to as the most significant bit, because since we're going left, the numbers go up and they rise quite quickly, because we're talking about exponents, and we're talking about rising here of powers functions. So as we go left, the numbers go up quite fast. It's an exponential function as we go to the left. So the more you go left, the more significant you affect your value. That's why the left side is usually the most significant bit and the right side is the least significant bit. In this example we have 6 digits, and we can see that we're starting with 2 in the power of 5, which is 32. We can only make it times 0 or times 1, because that's the only digit that can fall into place. But surprisingly, with this representation we can build pretty much any number that we want. Yeah, we already know how we just saw how numbers are converted from binary to their decimal representation. So we can know that each binary digit represents in its place 2 in the power of the place. So the first is the 0, then 1, then 2, then 3, and we can construct the number back from the digits. So far, so good. Going back, we could actually divide the number by 2, and we can see if we have any remainder with the division by 2. And that's how we can go from the most significant, actually we are going in the opposite direction. Since we're going from the high numbers here, we are constructing the numbers from their lowest remainders. So if we take a number and we start dividing it by 2, we can construct on every part of the number the binary digit that corresponds to its place. And that's how we can get, as you can see here, from 500 to this representation. That's the trick. Is that okay? Mm-hmm. Hexadecimal is used for containing more data in one place, data which is usually represented by binary data. In hexadecimal we have 16 symbols. So we are counting on the base of 16. Hexadecimal means 16. How is this done? We have the regular numbers, the decimal numbers from 0 to 9, which are the ones we use in decimal, and then we have to add 6 more. We have to add 6 more, and these are represented by the letters from A to F. Usually in notation, it's also the way to put it in a program. We represent hexadecimal numbers with a prefix of 0x. So we can see here how each of the digits of the hexadecimal notation corresponds to a specific number. So F is 15 and 0 is 0, and that's the sequence. Constructing numbers is just the same as we do in every other method, only that every part here is represented by the power of 16. So the first number would be 16 in the power of 0, then 16 in the power of 1, that means 16, then 16 in the power of 2, and then 16 in the power of 3, and this climbs up much faster because we're dealing with much higher numbers. So if we look at the number 9786, we can see, let's start from the least significant, which is 16 in the power of 0. That means we have 6 times 1. And then we have 8, which we are multiplying in 16 in the power of 1. That's the second place. That means 8 times 16. And so on and so forth. That's how we construct the number. That exactly the same way. Anyone didn't know about this until now, by the way? Is this new to someone? Great. So the conversion is done exactly the same way as we just did with those numbers. We can take any of the digits and we multiply its value by the exponent representing the location of the digit. And that's how we can get from 4 times 1, and then F, which represents 15, and we multiply it by 16 in the first power, which is 16. Then we take 1, which is the leftmost digit in this case. We multiply it by 16 in the power of 2, which is 256. We sum it all together and we get to 500 decimal. And the same here, we have 2 F's, and we can see that each one of them is 15, but we are multiplying it first by 16 in the power of 0, that means in 1, and then we're multiplying it in 16 in the power of 1, that's 16. So we get 240 plus 15, that would be the number. And that's actually representing a number which is 32 bits. And That's the highest value of 32-bit number, 255. We have 256 different numbers in 32 bits. Going backwards, so just like we did with the binaries, we are dividing, but since our counting system is divided by 16, we're dividing our number by 16 every time, and we're checking the remainders. So in this case, we are taking the number 500, we're dividing it by 16, we're getting 31, and we have a remainder of 4. So that 4 will go to the least significant point. Then we're taking the remainder, 31, we're dividing it again, we're getting 1, and yeah, 15 is the remainder, so it represents by F, and so on and so forth. This process is also quite automatic. I mean, this trick is not much of a trick. If we want to convert a hexadecimal directly to binaries, that's even easier, because every number in the hexadecimal can be represented directly by a 4-bit number. So each one of the numbers from 1 to 15 can be translated directly to a binary number. So if we have F in our number, we can put just 4 ones immediately, and that's quite easy to know and to remember if you're into that. Numbers, well, we have some numbers which are represented by 16, we have numbers by 32 bits, we have numbers by much more. We've seen them in the previous part of the course. And again, these numbers are usually represented in the real hardcore. They are represented in binary format, and these could be converted back and forth to any counting system. So in this case, we are representing the number 100, and we can convert it back to a binary breakdown of the number, and we can construct a binary number which sits exactly in 16 bits. So we can know that the first part that we have to turn on the 1 is the 4, which means the third place, because this is 1, then it's 2, then it's 4. The second bit which we have to turn on is bit number 5, and then bit number 6. In a 32-bit number, this will work exactly the same, only that we will have more space to store data, and our number will have more trailing zeros if it's small. But the idea is exactly the same. If we have a character, again, characters are usually represented by their value, by their ASCII value or Unicode value, depends on which system we're working on. And again, we are taking the value and we're just storing it in binary format, just like the others. So far? Great. If we have signed, I think we also mentioned that when we were talking about variables, we have signed variable types and we have unsigned variable types. They use the same space and they use the same amount of bits. So if we have an int or we have an unsigned int, they are actually using the same space. And that means that we have to tell whether the number is signed or not. The usual way to do that is to use the most significant bit, the leftmost bit, to represent whether a number is positive or negative. And in cases that we have numbers which are unsigned, then we are using this bit as part of the number. That's why we have numbers which are from 128 to minus 127, or we can use the whole range and then we can use it from 0 to 256 in those cases. So in this case, we can see that if it's a signed now, if this binary number represents a signed number, we can know that it's positive. If all the bits are 0, this represents the 0 number because there are no bits turned on, which is counted as a positive number since the bit is turned on as 0. The signed bit is turned off. And in case that we have a signed number, the leftmost bit is turned on, and we can know that this is a minus sign. If we are talking about if we're talking about numbers which are what's going on here? If we're talking about numbers which are signed, that means that we are reserving the leftmost bit for the sign, whether it's plus or minus. That means that we have all the other bits to use for the numbers. In that case, if we have a number and we want to represent the highest number possible, we have to turn on all the other bits and keep this bit, the first bit, turned off. So that's how we construct. That's how we can construct the highest positive number in a signed kind of variable. If we want to represent the smallest negative number in a signed variable, we do it the other way. We put the 1 in the signed bit, and we are putting zeros in all the other bits. That's because in most computer translated variable systems, the calculation is done in such a way. There is a subtraction of the current representation of the variable from a specific number. Again, these are examples representing numbers with greater volume, but again the system is exactly the same. To represent the highest number, turn off the leftmost bit and turn on all the others. To represent the lowest number possible, do the opposite. So again, we're talking about 8-bit numbers for the simplicity. We can count them from 127, which is the highest number when we're talking about signed. We're going to the 0, which is also counted as signed because the signed bit is turned off. And once we turn it off, once we turn the bit on, we're going actually backwards to get to the lowest possible number, which is minus 128 in this case. Any more about this? I mean, these rules are pretty much straightforward. Now, floating point numbers are a little more complicated to represent. The whole idea of floating point is that we have a decimal point. That means that we have a fraction, and that means we have to represent our number in a way that can contain the fraction. We have to know where the point is put, and we have to know whether it's a negative or a positive number. Now, there is a standard called IEEE 754, which codes how exactly these numbers should be represented. And the idea is in most systems is the same, and in this specific standard, it only says how and what parts of the number are divided for what. So in this case, what we have, again, the leftmost bit is representing the sign, whether we're talking about a positive or a negative number. Then we have a part which is called the exponent, which is the actual part where we are, since we are going to represent this number in a binary format, we are taking it by 2 in the power of something. These numbers represent what this power is. I'm going to show a more detailed example in a minute. And then there's the part called the fraction, which geeks like to call mantissa, which is the other part of the number. I want to show a more detailed example of what it is and how it's really constructed and how it's represented in memory. And I think it might be more clear in this case. So here's a nice number, minus 16.000185. What we have here is the representation of this number. So the first bit, the yellow one, represents whether the number is positive or negative. And in this case, we have a negative number, so this will be turned on. The other part is the exponent. You can see down here how the calculation is being done. So we have the symbol, which is the yellow part. Then we have the exponent. The exponent is used in this, in the IEEE standard in this way. We're taking 2 in the power of exponent minus 127. And then we're taking this result and we're multiplying it by 1 point, the number which is represented by the mantissa. It's not exactly intuitive, but that's the way. So the mantissa part, by the way, which we can see, which is starting from the 9th bit and going on to the 32nd bit, actually from 10 to 32nd, which is from 9 to 31, is calculated like we can see up there. This is bit number 9, so this represents this bit, and it's actually representing 2 in the power of minus 1. That means 1 divided by 2, which is actually half. The next bit is represented by 2 in the power of minus 2, then 2 in the power of minus 3, and so on and so forth. So in the end, we have to take a look at the sign, we have to calculate the exponent, and then we have to calculate what the fraction is, and then we have to calculate it all together to construct the full number. So in this example, for example, we can see, let's put everything in place. We have a minus sign, which means that the leftmost bit is turned on. Then we're taking the part of the exponent, which is this, and we're making a calculation of 127 minus what this represents. Then we're taking all this and we're multiplying it by 1 point, whatever the mantissa contains. So if we put it all into decimal numbers, this would be the result. So we have this number of the exponent is representing 127. Sorry, 131. And that means that the value here will become 4. Then we're calculating the mantissa part, so we have 2 in the power of minus 17, then half in the power of minus 18, then half in the power of minus 23, because we're going from left to right. And we can convert these into real numbers, so this will be the result. We have to put by force 1 point to every one of them, so the result here will be this, and we have to add 1 to it. And in the end, we are multiplying 16 by the result of what we get, and that would be this number. Not very intuitively easy to construct this from that, but I made this small demo because I don't think it's very clear from here, and I think that if you go to Wikipedia and start reading about floating point representation, there might be some brain explosion going on. And I've seen much more. If you're looking for better understanding of the floating point representation, there are other tools online that are maybe better to use. I think I've also encountered There is some Java site. I hope I can run it. Yeah, that gives the whole process with explanations, and you can turn on and off bits, and you can see how they affect your number. So you can see all the representation possible. You can see what each one represents. You can see representation of binaries and hexa and decimal and all that. So that could be quite useful if you really want to do that. One more word about representations. Of course, all of you know the calc, right?
Mm-hmm.
And you all know that calc has the programmer part, which can convert numbers from decimal to their octal, to their hexadecimal, to their binary, and you can switch how big those numbers are represented in memory and how accurate they are. So this is also a useful tool. I want to build a very small project because we don't have this. We don't have much live demos today, so I'm going to make a very quick one, which is going to contain almost nothing. Okay, let's put an integer x and assign it -50, and let's break. Okay, we'll look at that later. You all know the watches window, right? When we are debugging and we have a breakpoint and we can always see what's going on with our variables. So if I put here x, I'll see how it's represented. Visual Studio, not all versions of Visual Studio, but from 2008 and on, I think, added the option to change here to hexadecimal display. So I can actually see how my number is hexadecimal formatted. And if we go to the debug windows, under debug windows, sorry, I have no mouse today. There are 4 memory windows that you can open separately, and these memory windows just show really what's sitting in memory by a specific address. We can see the address of the variable if we put a reference to it, and reference is done by the ampersand. So this is the memory address where this variable really sits. And I'll go back to the memory window, and I'll put the reference to the variable. And we can see that this represents, oh, what did I do? Here's the representation of my number. What the? Last time. Here's the representation of my number. And we can verify that if we, for example, open calc and we put a -50, and let's put it in hexadecimals. We can see that we have the CE and then FF, 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 and all that. So here it is, the CE and then the FF, FF, FF. And since we're dealing with the number which has only 1, 2, 3, 4 times, yeah, 32. So that's because the memory addresses are read in this direction. But if you really want to see what's going on, you can actually really inspect your variables on the very low level, if you really want to do that. And if you want to know how they are represented in hexa, you can also do it directly in the watches window. There's no way to see here binary representation. Maybe there's a plugin to do that, but not that I know. And note that when I'm going back to normal decimal representation, we still got the address represented as hexa. So that's our very little demo. Questions so far? There are much better, if you really want to dig into the IEEE standard of representation of floating point numbers. It's a heavy topic, but there are nice videos also on YouTube that explain with nice lecturing how they are constructed, and there are much better documents, including this one, which actually explains how these things are constructed, much better than going to Wikipedia. So this link, don't go to Wikipedia for that. Texts, well, in the computer world, we are always representing as binary data, so texts are also represented as binary data, and each character in the text has a code. And in the old times, they used to have 8 bits, so that means 256 different types of characters. Of course, unsigned, because having signed numbers representing characters doesn't make much sense. And then they wanted to represent much more, and they came up with a Unicode standard, which is twice as much space. It's 16 bits per every character, and it should contain pretty much all the characters and all the alphabets in the world, or so. And it's quite enough. 16 bits are quite enough to represent all the needed characters for any kind of text. So that's how it is. Each character has its own code, and of course in memory it's represented as binary code. So the letter A is represented by the number 65 according to ASCII standards, and ASCII, by the way, is American something something character something something. Yeah. American Standard Character something something. Internet International something. We're getting closer. Okay. So that's it. Not much to say about characters, right? They're quite something. Strings are collections of characters. In C and C++ and related languages, characters are strings are just a collection of characters in memory, like an array, and they are terminated by the null character, the zero, the nothing. Where nothing exists, there is a character that contains the absolute nothing, which terminates the string. However, in more modern languages such as C#, they are represented by an array, some kind of an array, which we have also a part of it which tells how long it is. And the beauty of that is that actually, if I'm not mistaken, C# texts and strings can contain null characters inside them. I mean, in C++, once you have a string, once you reach the null character, that means you're done and the string is cut. But in C# you can actually construct strings which contain null characters inside them. And the encoding of the characters could be either 8 or 16 bits, and all the modern operating systems and development environment and C#'s default and everything is now supporting Unicode by default 16-bit characters. So your string, as we've seen also in previous demos, can contain all kinds of international characters in them without doing much work. In the previous world with C++, this would have been a little bit more work to represent Unicode texts. Have I been running too fast or too slow? I don't know. Anyone wants to ask something? Okay. Don't rush it. Take your time. Think about your questions. You can grab a coffee. I told you it's going to be short today, and it's going to be quick. And most of what I'm going to talk is, you know. I hope that that from the next lesson next week, I'm going to talk about new things that you don't know, and that's going to be a lot of fun because we're going to start diving really into the hardcore of the object-oriented parts of C#. And I'm not just saying it's going to be fun. It's going to be, yeah, classes. So didn't stop. So that's it, I think, right?